in this problem, we want to minimize the surface area of a can, of a cylinder can, kind of like maybe a soup can. And the point here is that the can must hold 1 liter of soup or whatever is going to be in the can, and 1 liter is actually 1,000 cubic centimeters. So we want the can, a big giant cylinder can, we want it to be able to hold 1 liter, but we want the dimensions of the can that minimize the surface area. And so that means we're going to minimize the amount of materials that it takes to make the can, like the metal that you use for the can. And of course you'd like to minimize that because you save money and cost. And so, but we do need it to hold 1,000 cubic centimeters because that's what we're using it for. And so this 1,000 cubic centimeters is going to be a constraint because of course we can always minimize the surface area of the can by shrinking it down, right? So what we're going to do here, let's look at a cylinder and look at the formulas for the volume and the surface area, because we're going to use both of these. One is going to be what we're going to maximize, and the other is going to be the constraint. Okay, so you got a radius of the can, and then you have like the height of the can. Okay, and then the volume of this can, which we'll use V here, is the area of the circle times the height of the can. So the area of a circle is pi r squared. But then you multiply that by the height of the can, and that actually gives you the volume of the can. Okay, now the surface area, and we'll use SA for surface area of the can, it's the sum of the area of these two circles plus the material around the outside of the can. And if you imagine taking the can and cutting off those two circles and cutting a strip and laying it out flat, you would end up getting a rectangle here, right? So you have the two circles plus a rectangle, and this rectangle here would be like the height, and this would be the 2 pi r, which is the circumference of the circle, because you're going to curl that around and form the tube, and then you put the area of the two circles on there. So you get these two circles, and the area of a circle is pi r squared. So you're going to have two of those, 2 pi r squared, plus you're going to have the area of this rectangle. So that would be plus 2 pi r times h. So this is the surface area of the can, and this is what we want to minimize. Okay, and we want to find the radius and the height that's going to minimize the surface area of that can. Okay, so our constraint here, is that this volume has to be 1,000 cubic centimeters. So in other words, pi r squared is going to have to equal 1,000, or pi r squared h is going to have to equal 1,000. Okay, now when we look at this formula, it's going to be easiest to solve this for h, because that's just going to be h is equal to 1,000, and this would be pi r squared. And it's going to be easiest, and there's only one h in this formula, right? And so we're going to put this in for the h right here, and we're going to get the surface area all in terms of r. That's just the simplest way to get this all in terms of one variable. I could solve for r and plug that into here, but then you'd have everything in terms of h, but it's going to make things, I think, a little more complicated. And to know which one, I mean, you could do it both ways. It just takes, a little bit of exposure to doing these to know which one is going to be easiest. And you could probably get there both ways. Okay? So I'm going to plug this in for the h, and when I do, I get this. Surface area is equal to 2 pi r squared plus 2 pi r, and then in for my h, I get 1,000 over pi r squared. Okay, now some of this is going to simplify here. So my surface area is equal to 2 pi r squared plus, now the 2 times 1,000 would give me 2,000, and then the pi's are going to cancel out, and one of the r's are going to cancel out. So I'm just left with like 2,000 over r is what I'm left with. Okay, so that's not too bad. We can take the derivative of this, so let's do that. dA ds. And when I do, I get 4 pi r, and then this would be minus 2,000 r squared. Okay, so now I'm going to set this derivative equal to 0. So let's do that. So I get, so we're setting it equal to 0, of course. Oops. We're setting this equal to 0, of course, so that we can find the critical point, because we want to find the minimum value of this function, the r that gives you the minimum value. So let's find the critical point by setting this equal to 0. Okay, and maybe I can move that to the other side, so I get 4 pi r is equal to 2,000 over r squared. And then maybe if I put this over 1, I could like cross multiply, and I get 4 pi r cubed is equal to 2,000. And then I can bring that 4 pi down, so I get r cubed is equal to 2,000 over 4 pi. And then my r is going to be the cubed root of 2,000 over 4 pi. And you could simplify that, I guess, into the 4 would make that into 500, so it'd be like cubed root of 500 over pi. Okay, so now this is the critical point here. I guess you would have another critical point where this is equal, where the derivative is undefined and r is equal to 0. But notice if r is equal to 0, you wouldn't have a can at all, so it wouldn't include 0. And then I suppose this could, we'd just say that r here could go to, so 0 to infinity. So what we got to do now is we have to make sure that this is a min, right? Because just because it's a critical point doesn't mean it's a minimum. It could be a maximum, it could be neither. So I think, again, the easiest way would be to take the second derivative here. So dA over d, oh, and you know what? I have dA over ds. I'm not sure why I did that, but this would be like dSA, I guess, over dr. So that would be my derivative. So this should be like dSA over, I'm going to erase this. This would be d squared SA over dr squared. That's how you would write the second derivative. I was not very careful here. Sorry about that. But that would be the second derivative. And the second derivative here would be 4 pi, and the r would just go away. And then this negative 2 would go down and make that positive. So this would be plus 4,000 r cubed. Okay, so you would get this, and notice this is going to be positive, and so if you put a positive number in for r, this whole thing is going to be positive. So you could say that the d squared SA dr squared is going to be positive. In fact, for any value in this interval, this is going to be greater than 0. If it's greater than 0, it's concave up, which makes it a max, right? So r equals the cubed root of 500 pi is a relative max. And what we might want to do then, this is when you put in r, this is how you would want to put this into this formula here. And what I'm going to do is I'm going to just calculate these so we know what the dimensions here are as in terms of a decimal. So in other words, what I'm going to do is I'm going to take the cubed root of this. So 500 divided by pi raised to the 1/3. And so my r here is approximately 5.42. And now what I'm going to do is I'm going to put this into the formula for my h, which is 1,000 divided by pi times my answer squared. I'm going to use my answer button squared. So it would look like that. And so my height would be like 10.83. 838 or whatever. So this would be the radius here. This would be the height. That looks like it's double that almost, or very, very close. Because I rounded that up. I think it almost is double, because if I take my answer and I double it, nope, I'm sorry, I need to take this answer. Times 2. Yeah, it is double. So in other words, the diameter, which would be double this, the diameter and the height are equal in this case. That ends up being the case here. And I'm guessing all cans, like this is probably true with all cans, something similar to this. And that's why at the grocery store, oftentimes cans, often do have similar shapes to it. We got a feel for what a soup can is. They're probably minimizing the surface area. They might have some other conditions, that there are other factors that affect it too, like packing them into boxes so that you minimize the space on a semi-truck or something like that too. So there's probably other considerations as well. But this is a nice example here. So we're minimizing surface area for a given amount of volume for like a soup can, a metal can, something like that.